So in this video, we are going to discuss how to express repeating decimals as though they are fractions. Now, generally speaking, if we have a fraction and we're interested in turning it into a decimal, then the way that we do so is by dividing, for example, 3 into 1, and throwing out a bunch of additional decimal places over here. So it goes into 1 0 times, but it does go into 10 3 times with a remainder of 1. And then we get a 10 again, so 3 times with a remainder of 1, and so forth and so on. And this is how we can turn a fraction into a repeating decimal. We're actually going to be talking about how to do the opposite of that today. Now, when I take a look at the repeating decimal, 0.3 repeating, and I actually express this in terms of its decimal places, and this would be considered 0.3 plus 0.03 plus 0.003 plus 0.0003, and so forth and so on. Expressing them in terms of their fraction counterparts, this would be 3/10 plus 3/100 plus 3/1000 plus 3/10,000, and so forth and so on. Technically speaking, what you're looking at here is a geometric series. The reason that it's a geometric series is because to go from decimal place to decimal place, we would have to multiply by 0.1, or 1/10. So with that in mind, our first term is 3/10, and our common ratio is 1/10. The sum of a geometric series is supposed to take the form a over 1 minus r, and in that regard, this would be 3/10 divided by 1 minus 1/10. 1 minus 1/10 would be equal to 9/10, and multiplying top and bottom by 10 over 3, we see that this fraction reduces to 1/3. Now for this repeating decimal is known to have a period of 1 decimal place, because every single 1 place, we see that this thing is repeated. Now, in the event that you have something that is periodic with a period of 2, for example, so 0.57 repeating, so we would interpret this to be 0.57, 57, 57, 57, etc. Rather than expressing this in terms of tenths and then hundredths and then thousandths and then 10,000ths, what we're going to do is go every other decimal place. So the first 57 that we get would be 57 over 100. The next 57 that we get would be 57 over 10,000, or 57 10,000ths. The next 57 that we get would be millionths, and so forth and so on. We refer to it as periodic with length 2 because every time we increase the denominator's number of zeros by 2. This is a geometric series with initial term 57 over 100 and common ratio of 1 over 100 rather than 1 over 10. The sum of this geometric series, once again, is supposed to be a over 1 minus r, which would be 57 hundredths divided by 1 minus 1 over 100. That would be 57 hundredths divided by 99 hundredths. Simplifying the hundredths, this would be 57 over 99. Or you could reduce the top and the bottom by a factor of 3 to discover that this is 19/33. Now, it's also possible on problems that you'll have a portion of it that is repeating and a portion that is not repeating. For example, 0.58 followed by a repeating 3. What I would do in this case is separate out the non-repeating part and the repeating part. So 58 hundredths for the beginning, and then 0.00 with the repeating 3 at the end. Now, putting our focus on just the repeating decimal portion, this would be 3 thousandths plus 3 ten-thousandths plus 3 hundred-thousandths, etc. We notice that this is periodic with a period of 1. The first term of this portion is 3 over 1,000, and the common ratio is 1/10. So we'll retain the 58 over 100 as is. This will be 3 thousandths divided by 9/10. If we flip and multiply, we get 58 hundredths plus 3 over 1,000 times 10 over 9, which reduces quite nicely. The 3 over 9 will reduce to 1/3, and the 10 over 1,000 reduces to 100, leaving us with 300 in the denominator. For a common denominator, I'm going to multiply the first fraction by 3 over 3, so that we can have 3 hundredths for our denominator. 3 times 58 would be 174, plus the 1 from the second fraction. That'll be 175 over 300. Dividing top and bottom of this fraction by 25, we get 7 on top and 12 on the bottom. So 0.58 followed by a repeating 3 would be 7/12. Try some for yourself.